it is my privilege to introduce Judy Rackison, who is an astrophysicist at NASA, and she will be talking about General Coordinates Network, harnessing Kafka for real-time open astronomy. Welcome, Judy.
All right, thank you very much. So you're going to have a little bit of a different session here today. We're going to learn a little bit about astrophysics and why astrophysics is actually a great application for technologies and like data streaming over Kafka. So I'm Judy Rackison. I'm an astrophysicist, as she said, at NASA Goddard Space Flight Center in Greenbelt, Maryland. I study the most energetic explosions in the universe, gamma ray bursts, which I'll tell you about. Which are actually have been historically why we've even built this system and how it's evolved to serve other kinds of astronomical transients. I also work on NASA missions. I work on the Fermi Gamma Ray Space Telescope, which has been detecting all sorts of exciting energetic phenomena for the last 15 years. And over the last few years, I've also started working on not just science and studying these objects and missions that support them and future missions that could do the same, but also really essential infrastructure that we use for the worldwide community to observe these events, to follow them up, and to learn about them in real time. You'll notice that I had a co-presenter, Dr. Leo Singer, who's my colleague and our GCN lead developer. Fortunately, he's homesick with COVID, so he couldn't be here. So I will be giving this talk on my own. I will mention that he is our technical lead, so if you want to throw me some softball questions about astrophysics, that'd be great. Maybe not about all the technical details of our Kafka cluster, but I'll do my best. Okay, so the General Coordinates Network. So first of all, let's start talking about astronomical transients, and specifically ones that happen very quickly. You may look up the night sky and think that everything stays about the same except for the Earth rotating. But that actually couldn't be further from the truth. The universe and the night sky are incredibly dynamic. It depends on what waveband you're looking at and what kind of transient you'd observe. But regularly, both ground and space-based telescopes detect astronomical objects varying on timescales from milliseconds to days, weeks, months, years, depending on what's happening. Their detection and follow-up observations across the electromagnetic spectrum and through multiple messengers, which I'll come back to, happen quite regularly, and we need to coordinate. This requires worldwide coordination, open data, sharing of information so that we can learn the most we can about these objects before they fade away or change states or do something that we will lose information on them. Some of these phenomena you've probably heard of supernovae, but there are also novae, which are just smaller explosions, but in a completely different kind of phenomenon. Solar flares, the sun is active, it emits flares quite regularly. Gamma ray bursts, which we'll come back to more. Magnetars, these are a particular type of very strong magnetic fields around a stellar remnant called a neutron star, and neutron stars do all sorts of fun things in the universe. To even new kinds of transients, fast radio bursts. This is a phenomena that's really only been studied in the last 10, 15 years, where there are millisecond bursts of radio waves, and we had no idea where they came from. We're starting to learn a little bit more that those have something to do with, at least in some cases, some neutron stars and outburst. Some of them repeat, some of them don't, but it's a very young phenomena that there's a whole transient community that's just learning to explore. So when I talk about multi-wavelength and multi-messenger, you use your eyes, you see light. That is a tiny, tiny fraction of the electromagnetic spectrum, which extends from very long radio waves, and the radio band covers many orders of magnitude. Microwave radiation, infrared, which is heat, the tiny visible spectrum, ultraviolet, X-ray, and gamma rays. And in fact, gamma rays go about another 10 orders of magnitude off the side of this plot. We can learn about astrophysical phenomena and, of course, things on Earth, so studying different wavelengths of light. Many objects emit across the spectrum or at specific frequencies. There can be spectral lines or different shapes of their electromagnetic emission, and that we learn a lot about the objects and how they work from that. There are also multiple messengers. Multi-messenger astrophysics is really several fields that have come into their own in the last 10 years. With the first detection of gravitational waves, which are tiny ripples in space-time, in 2015. And this is an extremely active field of study. In fact, the gravitational wave network is under an observing run right now. And GCN, as you'll learn, is reporting those events and distributing them to the world. as well as particles that interact or barely interact with matter, like neutrinos, which are tiny little particles that have very low interaction with mass, such that there's the main facility that detects these is called IceCube. It's at the South Pole. And it has about 1 kilometer of ice where there are buried tiny little, actually they're pretty big, detectors that look for little signals of light as a neutrino comes in and interacts with the ice. And that's actually after it's interacted with the Earth. And from this, they can pinpoint the direction and energy of this original particle, and we're just starting to learn also about where those come from. And it has something to do with accelerating matter to extreme energies around supermassive black holes. Okay, so back to GCN. So a little history lesson here. GCN was streaming data before any of you, I'll say that, in some way, shape, or form. So you're probably all familiar with Hubble, of course, is the most famous of the NASA astrophysics observatories, and Webb that just launched a couple of years ago. But there were actually 4 great observatories. This is a big program in the 70s and 80s for NASA to launch. And the lesser known one is probably the Compton Gamma Ray Observatory. This was a massive observatory that had 4 instruments. There's an image there of it being deployed from the Space Shuttle Atlantis in 1991. And Compton had 4 instruments that covered a huge band in the gamma rays, including the burst and transient search experiment. That was one of the instruments. It detected transients from all over the sky and actually helped solve the mystery of the origin of gamma ray bursts, which are distant exploding stars, basically. So CDRO launched in 1991, and unfortunately, it had a hardware failure in 1992. The onboard recorder that recorded all the data and then was going to transmit it down over the next ground station pass failed. This would have been the end of the mission, super tragic, but it actually led to an opportunity. Engineers and scientists realized that they could use NASA's space relay network called TDRS to send data down in real time. And that created an opportunity to stream that data in real time and actually send that to the follow-up community and start observations with ground and space assets. In a rather contrived acronym, the BATSI Coordinates Distribution Network, BACADYNE, became the first version of this system. It was built to receive those alerts from the BATSI instrument and distribute those alerts worldwide in real time. And BATSI later became GCN. So here's a little chart showing the history. So there was that hardware failure in late 1992. The first version of BACADYNE actually had some sort of tape recorder and a telephone, and it called people and apparently worked very poorly, is what I've heard from its original developer, a colleague of mine, Scott Bartlemy. Soon thereafter, though, that was improved by adding email, this newfangled thing, fairly new in 1993. And later, just a few months later, a computer-to-computer socket connection to distribute and stream those alerts in real time. And, alphanumeric pagers also were helpful to receive those informations and repoint your telescope. Now, I don't know where you were in 1993, but I was a child, and I think that's about when my parents got dial-up internet, and we had AOL. And so that was the kind of technology that was there. But some intrepid young scientists at NASA, colleagues of mine who have actually, most of whom have recently retired, we're streaming data from space all over the world. So it's pretty cool. So GCN has evolved, and I'll get into our latest incarnation, which is where Kafka comes in. But it has been serving alerts to the international astronomy community for the last 30 years. It utilized public internet infrastructure before such applications were common, long before the iPhone, long before any of the applications that any of us are working on now. It still serves as the backbone of several astronomical communities, and so I should refer here to the legacy system, which we're now calling GCN Classic. GCN has evolved, it's had a bunch of different names. After it started adding new instruments, not just BATSI, but the RXTE and Alexis. Those are a Rossi X-ray timing explorer, and Alexis was a UV mission. It became the Gamma Ray Burst Coordinates Network. It was just distributing gamma ray bursts. There was an additional service called GCN Circulars, which I'll explain shortly, that started in 1997. It then evolved to include other kinds of transients. It became the Gamma Ray Coordinates Network. And just to keep reusing the acronym, we're now calling it the General Coordinates Network. So the GCN Classic system is still operational, and part of what we're doing is transitioning this to a new cloud-based, Kafka-based system. The old system, though, runs on premises at Goddard. It uses custom data formats and protocols and lots of manual account administration, which actually I'm doing these days, so I'm looking forward to us transitioning beyond it. There are two types of data products that we distribute via GCN: GCN notices and GCN circulars. Notices are generally by and for machines. They have a fixed predefined format. It has been that the schema are specific to each notice type, and this is something we're trying to generalize, especially for machine readability in the future. And there are GCN circulars. These are generally, they're human-written astronomical bulletins, so a sort of quick publication. They're by and for humans, although some teams have gotten clever and have written scripts that automate them and that work most of the time. They have a free-form text, though, with an established style. We have a whole style guide, and they are citable in journals, but they're not peer-reviewed because we distribute them immediately. So NASA's fleet of astrophysics observatories, I don't know if you can read this, but there are certainly a few familiar ones on here: Hubble, Webb, Chandra, maybe. Hopefully Fermi, that's one of the missions I work on. But there are many missions that have been flying for a long time. I mean, Hubble, it's been more than 30 years. Chandra has been 2024. Swift, which is a mission that's very important to what GCN does, has been almost 20 years, and Fermi 15. But there are many new missions coming, both mid-size and bigger missions, but also lots of tiny missions. There's CubeSats, which are sort of pocket-sized satellites. In fact, I work on one of these missions, BurstCube, which is about the size of a shoebox, and we're launching that next spring. There are also ISS payloads that have instruments. And anyway, there are many, many instruments coming. These are the instruments that right now produce GCN notices, so those machine-readable, automated alerts. Swift and Fermi are really the powerhouses here, and these are just NASA missions. There are also ESA, JAXA, other international missions that produce notices, as well as ground-based observatories funded by the National Science Foundation, the Department of Energy, and others. But a lot of these missions that are coming in the next few years are lots of these small sats, and so this says something about the scalability of our system, that we need to be ready to have many new producers sending things to it, and not just sort of the same few. GCN circulars, there are many more missions where users of those facilities have done observations and reported through the GCN over the years, especially when it comes to some of these very exciting astronomical transients where everybody gets involved. That covers actually most of the missions also that are coming. These are the logos of all the missions that currently produce notices through GCN. I mentioned Swift and Fermi already. Integral is an ESA, so European Space Agency mission. Agile is an Italian mission. GECAM is a Chinese mission. We have the gravitational wave network, LIGO, Virgo, Kagra. LIGO has two detectors in the US, Virgo in Italy and Kagra in Japan. HAWK is a ground-based gamma ray detector in Mexico. We also have IceCube, I mentioned already at the South Pole, Super K, which is Super Kamiokande in Japan, and SNOOS, the Supernova Early Warning System. These are the systems that will tell us when there is a supernova in our own galaxy. We are overdue, and we are very excited for one to happen in our lifetimes. The last one that was anywhere nearby was in 1987, and it was still exciting, but we would like a galactic supernova, not too close, but close enough that we could study it. And there are also, anyway, a number of other detectors, I don't need to go into all of these, that currently report through GCN notices. So how does this work? Something goes boom in the sky. Really, these things are very far away, so they're not really that bright. But they are certainly detectable by our sensitive telescopes in space. Say it's a gamma ray burst, it's seen by Swift and Fermi. In fact, I've been getting messages from Swift. I don't think they're real. I think they're having an issue with where they're pointing, but I've been getting messages in the last half an hour through GCN from the Swift Observatory. Swift and Fermi send out alerts through NASA's TDRS system. We get those within, 10, 20 seconds. They get sent through GCN and then distributed to the world, to any public subscribers. Ground-based telescopes might say, oh, I can look at this right now, I'll go repoint. I mean, there's more complications in terms of proposals and observing time and that sort of thing. But there are also robotic telescopes that will automatically repoint. And then these transients evolved over the coming hours, days even, and observations will continue. And that information is shared throughout the world through the GCN circulars and the notices. So here's an example. I've been talking about gamma ray bursts. So what are these? These are I think, the most exciting astronomical transients. They are bursts of gamma rays. We're bad at naming things in astronomy, but that was initially what was seen. This is due to either a very massive star that suddenly collapses to a black hole, or it's due to the merger of two stellar remnants, these neutron stars that went supernova at some point. They stayed in a binary, and a few billion years later, they merged together. We see both types, so, and they have some different behavior. What happens, though, is they produce a new black hole either way. It produces a relativistic jet of material. It starts interacting with itself and its surrounding environment, and it produces a signal in the gamma rays that can last from a fraction of a second to minutes, followed by a multi-wavelength signal across the electromagnetic spectrum that can last hours, days, even years in some extreme circumstances. Often these things are poorly localized, so that requires a lot of community coordination. So localized on the sky, that we just know, not that they're precisely right there, but that they're over there somewhere. And so that presents some challenges in terms of follow-up observations. They're fading quickly, they're rapidly evolving. And there are many instruments that need to follow these up and be coordinated, and I think you're starting to see where Kafka comes in handy. This is an example timeline of a burst from last year, from October 16th, 2022, which is one that I had made the slide at some point for. There's a burst of gamma rays, which is that first plot is just showing you. It's a bright signal. A GCN notice comes out that says, we saw it, this is where it is, here's some basic characteristics. The Swift Observatory actually has multiple instruments on it, and it repoints with the narrow field instrument and characterizes it in UV optical and X-ray. They find a good position, they get an arc-second localization, that's good. And then some ground-based telescope did observations, and here's them reporting on it. So there are many, thousands of examples of events like this, but this is one of those timelines. So you can see things are happening kind of seconds, kind of timescale minutes, and this is streaming data as fast as possible is really important here. Here's another example. This one led to a Nobel Prize in physics. The detection of gravitational waves from merging neutron stars. This happened in 2017. I hope you've heard of this. There was a lot of press on it at the time. There was initially, the gravitational wave network saw a signal of a merging neutron star. Coincidentally, Fermi and the Integral Observatory were just doing their thing, monitoring the sky, and they saw bursts of gamma rays a couple of seconds afterwards. It was quickly realized as these alerts streamed through GCN that these were the same event, even though we didn't have a very good position of them at the time. This led to an enormous follow-up campaign by more than 70 telescopes were involved in some of the initial publications. And about 12 hours later, it was pinpointed quite precisely. The host galaxy was found, and we've been observing it actually for several years, even since then, in the radio and the X-ray as this transient evolved. And we've learned a ton about these objects, about extreme physics, all sorts of things from this event. We've even learned something about the origin of the elements. So if you walk away with nothing else, know that everything in you that is not made of hydrogen or helium came from dying stars, pretty much. So this is the astronomers' periodic table. And you can see that merging neutron stars, which are the ones that are in yellow, is where lots of the heavy elements in the universe came from. If you're wearing jewelry, nice jewelry, I guess I should say, it came from neutron stars merging billions of years ago. So that's just a fun fact for you. Here's another example, a neutrino. I talked about these little particles that barely interact, but they come from extreme systems. Also in 2017, there was some high-energy neutrinos detected by the IceCube Observatory, and with a large follow-up campaign across many observatories, it was determined to come from a particular flaring supermassive black hole at the center of a galaxy called a blazar is the type of source. This required a lot of coordination because it actually had been flaring for a while before these neutrinos were detected, and required a lot of follow-up effort and coordination for this, and some of this happened in the GCN. So the scientific landscape has been evolving since GCN was first created in the early 1990s. Gravitational wave event and using GCN as the primary distribution mechanism was, starting in 2015, required a huge amount of development. Examples of high-energy neutrinos, like the one I just mentioned. A couple other fun source classes titled disruption events. This is where stars get eaten by supermassive black holes, create jets briefly, fade away. Magnetar giant flares, these are these extremely strong magnetic fields, neutron stars. We see some of these in our own galaxy. In fact, we're overdue for one of those too, which would be pretty cool. The last one was seen in 2004. This is where it goes into an outburst with a large flare, and it has lots of gamma ray and X-ray emission, and those are fun. We've also seen a few handful of these in other galaxies. I know these slides will be posted, and I put in a link. There's a really cool animation of what all the emission components. This is a still from that animation from the binary neutron star merger, and I encourage you to check it out. But if you also just Google NASA neutron star merger, you'll probably find it. The technical landscape has been changing. GCN Classic was revolutionary in the early 90s, but it hadn't actually changed a whole lot until a few years ago. And astronomy is learning to learn from industry about developing things like general time series databases and streaming frameworks. We don't need to develop that ourselves. This stuff exists because there's lots of commercial applications for it. The Rubin Observatory, which is coming online next year, this is going to be a facility that is going to revolutionize optical transient astronomy. They're going to detect something like 1 million transients a night, which is a fire hose of information. Most of those won't be that interesting. They'll be variable stars, asteroids, things that aren't varying, really, that won't require follow-up observations. But the Rubin Observatory they decided years ago that they are using Kafka to distribute their transient alerts as their primary data product. And that they have a group of sophisticated brokers, or data brokers, that receive that fire hose, distill it down into different kinds of interesting things so that people know even where to begin to follow up. GCN is not serving as one of those data brokers, but we do want to work with what comes out of them so that we can correlate with especially what we see in the multi-messenger and high energy sky. There are several other facilities that are also following suit and using Kafka, including us, as well as this Wiki Transient facility, which is a precursor optical survey, and things like the gravitational wave network, like over Gokagura. There are other projects, as in this morning in the keynote, Joe Froster briefly mentioned, he's in the back there somewhere, that there are some other projects at NASA that use Kafka, and we've have sort of a grassroots group of projects where we're trying to learn from each other in how to use Kafka, especially in the challenges of being inside a government organization and our IT rules and infrastructure. So GCN is the one project at Goddard, as I'm talking all about. There are also at the Jet Propulsion Laboratory, they have some enterprise information services, as well as there's some use for the Deep Space Network, which is one of the NASA's communication networks where missions outside of low Earth orbit, that's basically how they all get their data down through some giant radio dishes all over the world. And NASA Ames, which is not far from here, is using Kafka for some sort of air traffic management. If you have questions about these, you should ask Joe, not me, because he knows more about them. All federal agencies, though, are using self-managed Kafka brokers, either Apache Kafka itself or Confluent platform. We're using Confluent platform in GCN. We've been hearing today all about Confluent Cloud and all these wonderful features. We look forward to using that someday, but at this point, we are undergoing the process called FedRAMP, which is a government approval process to use cloud services on government systems. So Joe is actually leading that effort, and GCN is sponsoring this. Once this happens, and it can take years, it'll make it so that Confluent Cloud can be used by NASA and other federal agencies to use Kafka as a software as a service. So the new GCN, finally the General Coordinates Network. We have a new web portal and a new website, gcn.nasa.gov. I have stickers, by the way, afterwards, if anybody wants any. It has our URL and not much else, but feel free to grab some. We have one of the features of this. We can it's self-service, no more manual curation of me receiving emails from users and having to edit their accounts, which was fine in the 90s, but is not okay anymore. So it's all self-service. We're using open standards, Kafka. It's all open source. We've gone through the process, the challenging process to get NASA to give us an open source Git repository, and we have Git organization where all of our code is. It's highly available. We're running everything in AWS. It's secure. And we're working on expanding the producer instruments for GCN notices and also expanding into other areas in astrophysics for other transient classes. And we have future expansion plans for databases and web applications that build upon what we have now. So I mentioned GCN Classic. It distributes data in 3 custom formats over 3 custom protocols, which is not ideal. VO Event, this is created by the International Virtual Observatory. It's an XML-based format. It works fine. Some people in our community actually still very actively use this, but it uses a custom transport protocol, which has some problems. We have a text version that just goes over email, and then we actually are still supporting email because that's what a lot of users want. And a 160-byte binary format because I think that's what fit on a pager at the time. So there's some history in here. It uses a custom socket protocol that is used by a lot of robotic telescopes. So the first thing we did is we ported all of those formats could be received over a single protocol over Kafka. And that's what we call GCN Classic over Kafka. And that has been in production since mid-2022. That supports users, and I'll show you actually, I'll walk through a little bit about how that works. To receive any of those formats for any of the notice types over Kafka. And we're transitioning to our ultimate system, which we call GCN Kafka, which is where we will ingest data via Kafka and also transmit it to users all in JSON format. And we're working on a sort of unified schema so that most of the messages can be parsed in a similar way as much as the instruments are similar to each other. And it's going to take a while to do this transition because these are old missions without a lot of funding and largely, and it works. They don't want to fix, if it ain't broken, don't fix it. So we want to convince the community and our community of users to start moving to these JSON format over Kafka and adding the benefits. All new missions will use that, so I think that'll be a good carrot to get people to move over. Just a little bit about our infrastructure. So currently, data gets sent from observatories, from space or from some observatory on the ground. It gets sent to wherever their data processing facility is. It's sent through some either real-time things like TDRS, where it's a space communication network, or just some ground thing, even if it's in Antarctica. They use TDRS as well to send their real-time alerts. So they send those messages from Antarctica to space, and then received at White Sands. And anyway, transmitted data around. They process their messages. They send them to GCN Classic. GCN Classic via SSH gateway sends them to our Kafka broker. We have 3 Kafka brokers in our AWS system, where we also have single sign-on, our database, and our website. And then end users connect directly and can receive and stream those messages. Hopefully over the next few years, we'll gradually move everybody to not go through the GCN Classic part and just go directly through the new system, which will be more reliable and not depend on things like the machine that this runs on right now is subject to network outages in the building I work in, which are annoyingly frequent. So Kafka is not designed for this. It's designed for use inside an organization or maybe between organizations that trust each other. It's usually, it assumes certain things about the end user with Kafka client access. It assumes that the identity of your users is known to those who are setting up the cluster. It assumes that you trust those users and that you don't have very many of them. And in fact, apparently Confluent Cloud has a quota of 500 users. None of these things are true with GCN. So we use Kafka and the other astronomical data brokers that use Kafka as a public service. Kafka has supported OpenID Connect for single sign-on since this version 3.1.0, which allows us to totally decouple account provisioning from the Kafka cluster itself. And it allows us a practically limitless number of accounts. Limited more by, how much this costs us in AWS and such. It's compatible with numerous commercial and open source OIDC auth solutions. We use Amazon Cognito, and we use the same system for our website and Kafka broker to set other preferences and email subscriptions and such, and also the ability to submit things like GCN circulars. There are no custom auth extensions to sideload onto the server. Everything we need is in Apache Kafka, but fully managed Kafka brokers like Confluent Platform and Confluent Cloud come with lots of nice features, of course, that we want to use, and we're using Platform. You can try this yourself. You can receive Kafka messages from space. As I said, I was just receiving messages, getting through my phone to my watch a few minutes ago from Swift. you can go to our website, gcn.nasa.gov. I promise you this probably won't be as interesting as you think it is. It'll be a series of coordinates and numbers and maybe some plots that probably are fairly meaningless, but it's something fun to play with. And you can get messages from these space-based observatories and ground-based observatories. And we have a nice little quick start guide, which I'll walk you through if I have a few minutes. So you go to our website. This is what it looks like. I think this is a fairly recent screenshot, so it should look like pretty much what it does. And you can click on this Start Streaming GCN Notices. It'll walk you through the process. You sign in or sign up. And then you can do that with one of our single sign-on solutions. If you work for NASA or you have a badge, and that's what I would use to log in. But you can also use Social Auth, Google, or Facebook, or just an email and password via Cognito. This shows you're signed in. I think a lot of these screenshots are going to be a mix of Leo's screenshots and mine, depending on who did these screen grabs. But this shows that you're signed in and the mechanism you use to sign in. And then you can select credentials for your Kafka client credentials. And so you choose a name. So I have several of these, for whether I'm doing a demo or for my laptop or for a pipeline. You prove you're not a robot, and then you create new credentials. Then you can go in and select the formats you'd like to receive your data. Eventually, we don't have much offered in JSON right now, but that is where we're expanding with the new system. And you can then choose whichever notices from whichever missions or experiments you would like to receive. And this is the wrong screenshot. Sorry, you can learn more about those missions and what those notice types are. We have a missions tab on our site, and there's lots of details about what kind of content is in those different notice types. And these are written for professional astronomers, so this isn't really meant to be something that is just a place to learn about science. It's a place to receive real-time data, but it is public, and anyone is able to sign in. There is actually a community of amateur astronomers that does regular follow-up of sources and reports them. There's some organizations which they can do that, and there's a lot of people with some fancy amateur telescopes, and they can do some fun stuff. I think what I was trying to show with this screenshot is that, maybe I have that later. Okay, anyway, so you do that, you choose your notice types, and then you can collect sample, it'll generate sample code in a variety of languages, whether that is Python, Node.js, C, C#, whatever language you want. If you want a new language, you can ask us, and we may add it. We'll try to add it. And there's a Python package to install if you're using Python, and it'll pre-populate your client ID and client secret and all of your notice types, which then you can, of course, manipulate and add. You don't have to use our quick start guide, but this is just an easy way to get started with that code. We also have the ability, a lot of our users still want to receive email for these rather than necessarily streaming for Kafka. Kafka is meant more for pipelines, robotic telescopes, advanced users, I guess. So it's all powered with Kafka behind the scenes, but you can also sign up if you just want to receive email notices of these data types. Under your user account, there's an email notifications. There are a number of our users in our community over the last year have transitioned to using the Kafka system, and I've generally heard positive things, especially people can self-manage, and that's been a huge improvement. I know there are pipelines and instrument teams, some of these instrument teams I work on. Kafka powers a process where the Swift mission actually receives a notice from another observatory, uploads a command to the spacecraft within minutes, and then downloads an extra set of data to search their data and do subthreshold searches. And that's been partly powered by, that's largely powered by our system. There are coincident subthreshold searches looking in the gravitational waves and the electromagnetic that are using our system, and as well as automated and manual responses from ground-based telescopes. We have a lot of future development planned. In fact, we're funded right now through a directed program from NASA headquarters to do a bunch of development over the next few years. This includes, we're going to be distributing GCN circulars over Kafka, just as JSON records. Right now it's just email. But this is a service we have completely migrated over from the old system. We have a database of circulars, but we're also want to add a lot of capability to our database, a searchable archive of notices, where those notices get associated with the same event, astronomical event as the circulars. And we want to move all GCN Classic producers into using these JSON format notices. And I didn't go into any detail on this, but we have an alert schema, JSON schema that we're using to align those data types to be as similar as possible. And we want to make it simple for new facilities to sign onto our system, and also for users to use it to grow the community of astronomers that are using our system. And also we want to build correlators with other astronomical transient brokers, like the ones that reduce that fire hose from the Rubin Observatory. So thank you for listening. Here are some links if you want to check out our GitHub organization or reach out to us. And as I mentioned, I've got a bunch of stickers if anyone wants to come and grab them. So thank you very much.